I wanted to go over some of Chapter 20's information with you. So these are the notes that I took. So I will be looking at your notes and the reading quiz that you took, and I'm going to compare. You can compare yours to mine. We might look a little different. Some of you took way better notes than I took, um, but I do think that, like I said, I was able to pull out the things I thought were important. So in section 20.1, it deals with charges and forces, and they do a bunch of experiments with attraction, repulsion, and polarization. So with that, some big ideas. Conductors are objects where charges are free to move easily. You remember, um, conductors or atoms have electrons on the outside, protons, neutrons on the inside. So when charges are able to flow, it's electrons that flow, at least in solid objects. Insulators, charges are mostly immobile. Again, examples are, pardon me, rubber, plastic, dry wood, dry air, stuff like that. And like I say, the demonstrations that they talk about seem a little bit complicated, but I think if you read through those, experiment 1, 2, 3, I think they have experiment 4 as well, that really lets you know how charges are going to move when you have charging and discharging, conductors, insulators, things like that. And I think it's going to help you out with the physics classroom's interactives. One of the things I probably should do is do some electroscope demos with you. I think this is one of the last things I did in regular physics last year before we left. So remind me to do that probably soon. Okay, so don't let me forget that. Section 20.2 deals with charges, atoms, and molecules. So again, that takes a look at where the charges are in the atoms themselves. The fact that a conductor, you have positive ion core or ion cores, and the valence electrons, which are the outer electrons, are pretty free to move. Sometimes it's called a sea of electrons or an ocean of electrons, whereas in insulators, the valence electrons are quite tightly held. And by the way, in plasma and some liquids, positive ions tend to be the charges that move. But for us, we're going to think mostly of solids, and therefore it would be electrons. The Coulomb is the System International, or the SI unit of charge. That is equal to 6.25 times 10 to the 18th fundamental charges. Each electron and proton has one fundamental charge, or the reciprocal of that, which is 1.6 times 10 to the negative 19th coulombs. So the charge on an electron, negative 1.6 times 10 to the negative 19th coulombs. The charge on a proton, positive 1.6 times 10 to the negative 19th coulombs. You cannot have an amount of charge less than that and that can be isolated. Sub-subatomic parts like quarks can have partial charges, but one fundamental charge by definition is the smallest amount in this course that we can have. In section 20.3, it talks about Coulomb's law, so that's the mathematical representation listed here. It should look a lot like gravitational attraction, so Newton's law of universal gravitation, except that here we have a different constant, and instead of masses, we have charges. So this charge, K, is known as the electrostatic or Coulomb constant, is 9.0 times 10 to the positive 9th. Some places I've seen around 8.99 times 10 to the positive 9th. Newton meters squared per Coulomb squared. Excuse me. And while Coulomb's law will let us calculate the magnitude and direction of forces, since forces are vector quantities, we can superimpose these. So we can have multiple charges interacting with each other, and those will, the vector sum of those forces would be the resultant force. Newton's laws still apply. So we think of Newton's first law, second law, third law. Really, this is going to be an interactive set of forces between two charges. So we'll talk about that in class probably after the reading quiz if we haven't already done so. Section 20.4 is the electric field. This is an extremely useful way of thinking about things, and we'll have to talk about that more in the future. probably didn't get to much of that in first year physics last year because of the pandemic. I don't think that was covered in the AP1 exam, and I don't think we really talked about that in regular physics. So it's a real thing, first of all. You know that gravitational fields are real things because if you jump off the side of a cliff, you know that there's a gravitational force acting on you and you accelerate downward. So gravitation is a field force between objects with mass. Electric fields are forces between objects with net charge. So we have a general formula for electric field, which is symbolized by a capital E with an arrow, is equal to force over charge, F over Q. So that's the field at the location is equal to the force on a charge at that location. It's analogous to this. So when we think of gravitational acceleration, we think of a ratio of force to mass, newtons per kilogram. Here we think of a ratio of force to charge, newtons per coulomb. So source charges cause an electric field in space. Sometimes it's useful to think about the direction and magnitude of that field by thinking about something called a probe charge or a test charge. And it is defined as a small positive charge, called little q, to test the magnitude and direction of a field. So it's imaginary, and it's assumed to be small enough that the test charge would not change or affect the electric field caused by the source charges. So forces on a probe charge or test charge determine the direction of field lines. So field lines by convention or definition point from positive to negative, just because people have agreed on that. So that's how we visualize the electric field. Field lines show the direction of the force on a small positive test charge. They're opposite the direction of the force on a negative charge. So negative charges would accelerate against the field lines, positive charges would accelerate in the direction of the electric field lines. The strength of electric field weakens as one gets further away from a source charge, assuming it's a point source. We tend to think about the strength of electric field as shown by how close or far apart the lines are from each other. So as I said, in general, the formula for electric field is this. Since force, according to Coulomb's law, is equal to K, charge 1 times charge 2 over the distance between them squared for Coulomb's law, if we combine those two and say, well, this would give us the force between charges, then we find out that one of those charges tends to cancel out. And so the electric field at a particular point in space caused by a source charge is equal to the constant multiplied by the magnitude of the source charge divided by the distance squared of the source charge. So this is the electric field at a distance from a source charge or a point source. 20.5 deals with electric field lines and electric forces as being vector quantities and talks about multiple charges as causing them. We'll have some activities where we, in simulations where we look at these, but you're going to want to look at your textbook as well. Probably going to get you your 5 steps to a 5 soon also. A parallel plate capacitor is something that's going to be pretty important to us. It's going to be mentioned across several chapters and is discussed here. So that's made out of 2 electrodes, opposite charges on each plate. The electric field is uniform in between them. This is a formula on your formula sheet. This is a different constant. So it's called vacuum permittivity. That's a weird name. That's okay. We'll learn about another one later called vacuum permeability, which deals with magnetism. So this vacuum permittivity is 8.85 times 10 to the negative 12th. That Coulomb charge I talked about earlier is equal to 1 over 4 pi times this constant. There's reasons why you might want to use one or the other from time to time, and we'll get into those. So things we can assume about parallel plate capacitors: the field depends on the charge density. So in other words, how many charges per square meter there are matter. The field strength. It does not strengthen or weaken between the electrodes of the plates. So unlike a point source, the electric field between the plates of a capacitor is always the same strength. And that's assuming that what we call an ideal capacitor, which means the capacitor is much larger in surface area than the distance between the plates. There's an analogy between gravitational fields and electric fields and forces I think is super useful. So I've got some formulas here. I've got some visualizations here. So in a near Earth situation, we would have a gravitational field we'd show like that. If we had negatives in the ground, we'd show an electric field like that. If we had point source, meaning let's say we zoomed away from the Earth and looked from a spaceship, we would show our gravitational field lines like this. And if we had positive charge, we would show our electric field lines like this. So whether you have a uniform or a changing field depends to some extent on the perspective with which you're looking at that field. Notice here, the lines point away from positive. Here, the lines are pointing toward negative. Also, the closer you are to the object, the closer the lines are to each other, and therefore the stronger the field. So that's something that's indicative of field strength. 20.6 and 20.7 deal with some other aspects of the chapter. 20.6, the big idea is the electric field is always zero inside a charged or an uncharged conductor. So this explains why charges aren't moving on the surface of the conductor. Because if we go back to the formula we saw earlier, E equals F over Q, if we had an electric field inside or that was not perpendicular to the surface of a conductor, then there would be a net force that was at least to some extent parallel to the surface of a conductor, and those charges would move because they'd have a force acting on them. Therefore, since the charges on an object in equilibrium are not moving, by definition, the field on the surface of a conductor is always parallel to the surface, and there is no field inside a conductor. And that's true whether the conductor is solid or hollow. So that's actually pretty important. There's a pretty good diagram, figure 20.42 on page 720, which shows that the charges don't always have to be evenly distributed. That's similar to this. So the charges are going to depend on the shape of the conductor, where the charges are located, and the field strength at any point will depend on how those charges are arranged. But overall, still zero field inside here, zero field inside here. There is an effect called electric screening or electric shielding inside conductors, since you can't have an electric field. It means that if you have credit cards inside your wallet and your wallet has a little bit of a metal covering, and it can be mesh as well as a solid, that can prevent identity theft, because otherwise people can actually scan your credit cards from a distance, which is not good. You could have a metallic wrap key fob to prevent thieves from stealing the code when you press the lock or unlock button. A Faraday cage can be used to protect you or electronic equipment from electric shock. And a metal building can prevent electromagnetic waves from entering. And that means you would get very poor cell phone coverage inside there. Pickering High School Central is that way. The outer surface of the building is metal, not good for getting cell phone signals. I did not take notes on 20.7. The torque aspect is somewhat interesting. The DNA aspect is definitely interesting. And I worked in a lab, if you recall. But that particular part, and dielectrics they were talking about, and maybe diodes, I do not think that's a key part of the chapter. So with that, hopefully that helps out. I will do some example problems a little bit later.